Hello everyone, welcome to Electronics Prepper, the channel where we try to learn as much as possible about electronics to become more self-reliant with technology and prepare for the future. Today I needed to create myself a virtual ground from a single power supply because I will need to have a small signal taken from somewhere, fed into an operational amplifier, and well, due to various reasons, I will not have a dual power supply in the finished product that I'm trying to create. So I need to have it because my input signal is going both positive and negative. I cannot simply connect it relative to the minus of the power supply, so I have to create myself some sort of ground so that my signal can go below that ground. Also, since I'm going to be amplifying it with the operational amplifier, I'm gonna need it to well, obviously go below ground, so this circuit comes in very handy. And I thought, okay, let's make a short video because maybe some of you don't know about this. Now, I believe there are actually several types of such circuits that create virtual ground. So this is just one option, which is, in my opinion, the simplest one, because we are using only 6 components and all of them are cheap. They don't even matter that much. I mean, the model of at least of the transistors don't matter that much, so it should be a pretty nice and fast job that we can make when we have such needs. So the idea is very simple. Like I said, sometimes we have a single power supply, but we need 2 voltages, one positive and one negative, relative to a certain ground, where we only have an option of creating that ground and basically calling it virtual ground. So for this we have, now in truth be told, in its simplest form, we could just have a simple voltage divider created by 2 equal sized resistors, and of course in the middle we will have exactly half of the voltage across both of them. But the problem is that when we will come with a load, and the load will most likely load one side more than the other, then this point will fluctuate a lot and it will go up and down a lot based on the current that this load will draw. So just 2 resistors placed in series, like a voltage divider, is just not enough. So we need something a little bit smarter. And for that we have this circuit, which has 2 resistors, but also 2 diodes and 2 transistors on top. Small power transistors, small power diodes, because we don't need too big, at least if we are working with low voltages. And the principle is very simple. We are still creating a voltage divider here. However, we are feeding this voltage into 2 transistors, and we are relying on the transistors being able to offer current on the output, which is higher than the current that the resistors themselves can offer. So basically we're using the transistors sort of as amplifiers. We're using the fact that by injecting a small current in the base of an NPN of a bipolar transistor, whether it's NPN or PNP, doesn't matter, that transistor will be able to allow a much greater current to flow through its collector and the emitter. And that's exactly what we're doing here. So the idea is that, let me just make a screenshot so that I can draw some things on top of this. So we have here these 4 components placed in series, and the resistors must be equal sized. Okay, so this is mandatory. Both resistors must have the exact same value. Now, I'm not talking about them having a very low tolerance, but I'm talking about them having the exact same value in terms of how many ohms they have. And 2 diodes which will mirror the base emitter voltage of each transistor, but we'll get to that in a moment. So essentially, what we're doing is creating a bunch of smaller voltages here. Of course, each diode will, and by the way, this must be rectifying diodes, so not Schottky, not Zener, not anything else. I've chosen 1N40, 148 because they are the most popular and probably the cheapest, or one of the cheapest, and I think every electronist has some of such diodes in their lab. These hold about 0.7 volts across them, approximately. And let's say that, like in my case, I have a 15-volt power supply that I wish to split into 2 halves. Okay, so for each resistor, I'm gonna have half the difference between 15 and 1.4, which is both of these diodes combined, right? So I have 15 minus 1.4, and this divided by 2, so I have 6.8 volts across each resistor, right? 6.8. Excuse my really terrible drawing. I'm trying to do it fast, so I don't waste too much of your time. Anyhow, also, by the way, you hear me say point, but I'm actually drawing a comma. That's because in my country and in this part of the world, comma is actually the decimal character that delimitates, you know, the integral part from the fractional part. The dot is used for thousand separator, so it's pretty much reversed, as in, I don't know, in England, in America, or in the Western world in general. But anyway, you get what I'm saying. Basically, here in this point, we will have exactly half the voltage of the power supply. Okay, so I'm gonna draw these voltages on the outside so that I don't get too much dirt on the schematic. So basically here we will have 7.5 volts, which is exactly half of 15, half of our power supply. And of course, between here and the negative rail, we will also have 7.5 volts, which is exactly what we want. Now, we will feed these 2 points across the diodes to the base of each transistor, and then we will tie the emitters together. Each collector will go to each supply rails, and so the emitters will be our ground in the end. The voltages on each diode will mirror the voltages on each transistor, the base emitter voltage, and so this is why we have introduced these diodes, because they need to basically compensate for this voltage drop that transistors have. If we wouldn't have put them, then the basis of the transistors would have been at 7.5 volts, and the emitters, each transistor would have tried to place their emitters at 0.7 volts around these 7.5, and of course that would have been a failure. So yeah, this is why we need these diodes in the first place. And this is a pretty decent solution. We will be able to have here all sorts of consumers, or all sorts of loads, and we won't be able to draw too much current, but again, this kind of solution is the kind of solution that we will use when we need the ground more as a reference point, not when we will actually need to power some, I don't know, heavy loads on each of the voltages. So yeah, bear this in mind. Also, we need to calculate the resistors value, and well, that's also relatively simple. We know the voltages across them. We must find out the beta factor of each transistor and choose the absolute smallest one. And so we also need to know the maximum current that we want to pass through each transistor. I've chosen these very popular Beche 547, Beche 557. These are 100 milliamps maximum. And I've considered a gain of 100, even though they typically have more than 100, but just to be sure, I've considered the gain of 100. So we need to basically insert 1 milliamp into their base. So if we have 6.8 volts divided by 1 milliamp, that's 6,800 ohms. I've chosen the next value downwards, going downwards to a smaller value, and I've chosen 5.6 kilo ohms. It's a standard value, so that I'm making sure that I'm feeding a bit more current that it's needed to, you know, make sure that the transistors are working as best as possible. Now, if we apply, if we connect just one load to one of the voltages, this point will fluctuate a bit. It will go up and down, depending on, you know, how we're drawing the current. And I'll show you in a moment, because we will go to the workbench and we will do some practical measurements to show you how it works. But anyway, this is the general theory. It's not complicated, and it's a pretty nice circuit to know about. Again, when we have signals that change their polarity, and we need to feed them into an op-amp, and we just don't have a symmetric power supply. Okay, so now that I've explained the theory, let's go to the workbench and see how it works. Right, so here's what we're having here. We're having two voltmeters, one measuring the voltage on the positive rail, well, rail in quotation marks, because this is the positive half that we have created, right? The black one measures the voltage on the negative rail, and the yellow one on the right measures the current that we are drawing from wherever we are drawing it. And I'm going to, I have a load, an electronic load outside of the camera, and I will basically start drawing currents, and I will show you how these voltages go a bit up and down. Not a lot, but yeah, they don't they aren't able to stay very fixed. Anyhow, we have no load right now, and I have 7.46 and 7.57. This is due to the fact that I haven't really handpicked the resistors, so their value is slightly off relative to each other, but that's perfectly fine, because we don't care about super high precision whenever we are needing this sort of circuit. So right now I will be drawing current from the positive rail, right, and the negative rail will remain unconnected with anything on the output. So I'm starting to draw some current, and let's say I'm setting it to some 10 milliamps or so, 10, 11, something like that. The positive voltage has dropped a bit. I now have 7.3, and the negative voltage has increased a bit. I now have 7.7. If I'm drawing 20 milliamps, it has dropped again a little bit more, 7.20 something volts and 7.7 volts. The negative one. Right, and if I go all the way to the absolute maximum that I can, considering the power dissipation of these small transistors, which is right now 50 milliamps, I get about 7 volts on the positive rail and almost 8 volts on the negative rail. So this is how they shift. Shouldn't be a big problem, because again, we're not going to be drawing that much current out of only one of the rails. As a quick reminder, a typical op-amp, a usual op-amp, not one of those low power ones, but the usual op-amp consumes only a few milliamps, like 2 or 3 or something like that. So that shouldn't be a problem. And also an op-amp consumes current from the initial power supply rails, not from just half of the virtual rails. The virtual rails will only be used by auxiliary circuitry around the op-amp. So now I'm going to place the load across the negative. Just a moment, please. Across the negative rail, and you'll be able to see a similar but reverse effect on this. So now I happen to have an equal value of voltage, and I'm gonna start to draw some current from the negative rail. Let's see if I can make it around 10 milliamps. So again, I have about 7.6 and 7.4. This has dropped, this has increased a bit. 20 milliamps, let's see. Again, this has dropped a little bit more, 7.3 volts. This has gone up a little bit more, 7.7. You know, this is how it goes. And I'm gonna go all the way to 50 milliamps or around there. Again, I have about 7 volts on the negative and 7.8, 7.5 on the positive. The imbalance is not that great, considering what we're doing. So all in all, it should be a pretty nice circuit to know about, again, when we need a virtual ground from a single power supply. So I hope you enjoyed it. I hope you learned something new, or at least now you are better understanding how to solve this problem. Thanks a lot for watching. Those of you who can and want, I have a Patreon account. By supporting me financially, you are supporting yourselves, because the faster I can buy more gear and more components, the faster I can learn things, and the faster I can come with new videos to show you and to teach you what I've learned, and hopefully we can all get faster to that point where we can just do whatever we want in the realm of electronics. So thanks a lot for watching, and I'll see you next time. See ya!